Hey everyone, welcome back to part 2 of lesson 2, factorial notation and perms. Okay, so did we get those factorial notation into our calculator? Okay, and example 4, we should have gotten 74,046, and part B, 66,045. Okay, so and if you're not sure how it was entered in the calculator, you can check what I typed in up here, and hopefully we arrived at the same thing. Okay, so let us go back to the lesson. Okay, we're going to talk about the word permutation now. Okay, now you've actually been doing permutations already on lesson 1, but we were using fundamental accounting principle to do it. And really what a permutation is it's an arrangement of a set of elements in which the order of the elements is important. Okay, so basically when you hear permutation, you should think order is important. Okay? So situations like lining books up on a shelf, or the numbers in a phone number, or the letters in a person's name, or anything in which if you switch things around it would look different and it matters, then that's a permutation. Okay, so if order matters, we can do what they're asking here. John couldn't remember an access code except that it contained digits 3, 5, and 7. So the access code is 3 digits in length. Okay, and we would have 3 choices for the first digit because we know it's either 3, 5, or 7. Okay, and were they different digits? Let's read. Yeah, it contains the digit. So, and then 2 choices for the second digit because it would either be the other 2, and then 1 choice for the last one. So in other words, there are 6 different arrangements of 3 digits. All right, so we've been doing that all along. Let's take a look at the next page. An alternate way to figure out the number of permutations, or the list of or the number of arrangements, would be to use this formula that we're going to get into. First we'll write this, list all the arrangements of the letters of the word cat. Lovely. So C-A-T, A-C-T, C-T-A, C-8, nope, we've got C-A-T already. Okay, we've got A-T-C and T-A-C, or T-C-A and T-A-C. And I think that's it. So we have 6 different arrangements. Okay, write the number of permutations in factorial notation. Well, 3 letters. Okay, 3 choices for the first, 2 for the second, 1 for the last, which means in factorial notation that's actually equal to 3 factorial. Okay, so if you're taking all of the letters of a word, let's say, and rearranging them, the number of ways to do that is simply how many letters or whatever it is you have, factorial. Okay, and that comes in very handy actually. So example 5, we can put this to use. Determine the number of permutations of the letters of the word Regina. So 1, 2, 3, 4, 5, 6 letters of that word. We could do the fundamental accounting principle like we did on lesson 1, but we're just simply rearranging these letters. So using this idea up here, that would just be 6 letters, so 6 factorial. Good. Take a stab at what you think the next one would be. So 7 letters, in other words, number of ways, 7 factorial. Awesome. Okay, another situation would be if we have a word but we're not using necessarily all the letters. So let's say we have the word graphite. They want to know, first of all, using fundamental accounting principle, how many 3-letter arrangements can be made. Well, 1, 2, 3 letters. How many choices for the first letter? 1, 2, 3, 4, 5, 6, 7, 8, so 8 choices. Then I've used up one of the letters, so 7 left, and then finally 6. Now, whatever that works out to be. In the example above, we found the number of permutations of basically 8 elements taken 3 at a time. Okay, so we took 3 of the letters, made a word with it. And this is denoted by 8P3. Now, we tend to use for P, pick, to make it sound like we're doing something. So we have 8 things, we're picking 3 of them and arranging them. Okay, we'll get into combinations later when we also have that. Now 8 pick 3, we know from up here has to be 8 times 7 times 6. Well, let's think about how we could write that as a factorial quotient. Well, 5 factorial must have canceled off, so that must have looked like 8 times 7 times 6 times 5 factorial over 5 factorial, and we know on top that must be 8 factorial, and then we could think of 5 factorial as being 8 minus 3 factorial. So you'll notice 8, pick 3. Will that formula always work? Yes, it will. So this one is on your formula sheet. 8 things, picking 3 of them in our case, or n things, picking r of them. So let's use your NPR key on the calculator to figure out 8 pick 3, but it should be whatever this one was up here, should be equivalent to that. So let's grab the calculators. Okay, and we want, actually let's first figure out 8 times 7 times 6. Okay, so 336. We should get that number if we go 8. Now with this permutation notation, we have type 8 first. Then we go back to math, same place we got our factorial notation. So PRB, and then we want NPR, which is number 2. And now we have to type in what we're picking, so 3 of them, 8 pick 3. And there we go, 336, same value. Okay, good job. Let's take a look at the next page. Okay, so on this start of this next page, we have defining 0 factorial. Okay, because this is kind of a weird one actually. So if we use that formula and we actually take n things and pick n things to rearrange, we already know from that other page that, you know, if we had in the word Regina, we had 7 letters, so the number of permutations would be 7 factorial. So n things picking n at a time, we know is n factorial. But if we use the formula, that would become n factorial over n minus r, which is n minus n in this case, factorial. Now n minus n is just 0. So we end up with this n factorial divided by 0 factorial. Well, in order for this to still equal n factorial, which we know it has to, that would mean that 0 factorial would have to be 1. So that's what 0 factorial is equal to. Not 0, but 1. Okay, just something you need to remember. Okay, example number 6. In a region, vehicle license plates contain 2 different letters followed by 4 different digits. If the letters I, O, Y, and Z are not used, determine how many different license plates are possible by, first of all, fundamental counting principle. Okay, so we've got 2 letters followed by 4 digits. 1, 2, 3, 4. Okay, so let's start with the letters. I, O, Y, and Z are not used. So we'll take 4 from the 26 in the alphabet and we'll have 22 choices. It said different letters, so we can't use the one we just used again. And then followed by 4 different digits. How many digits altogether there are? There are 10. So 10, they have to be different. 9, 8, and 7. And then whatever that works out to be, that would be our answer. And we can get that in a minute. Let's pause the video. Okay, so big number. We should have gotten 2328480. Okay, now with permutations, generally speaking, that n pick r formula does not work all that well when you're talking about restrictions, like different letters and stuff like that. So, but we'll give it a try with this one. So 2 different letters. If it had said 2 of the same letters, we wouldn't be able to use the NPR formula. So 2 different letters. So we have 22 letters to choose from because we took 4 out of the alphabet, and we're picking 2 of them, okay? Times, and then we want 4 different digits. Well, there's 10 digits to pick from, and we want 4. Oh, sorry, I didn't mean to write a C. So we would have 10 pick 4. Okay, let's put that in our calculator, see if we get the same value. Okay, so pause your video. And sure enough, we got the exact same value by going 22 pick 2 times 10 pick 4. Alrighty, so we can write that in there as well. Okay, example 7. Algebraically solve the equation n minus 1 pick 2 equals 90. So when you see this n pick r in the formula or in an equation and we need to solve, think of your equation on your formula sheet. So n pick r equals n factorial over n minus r factorial. What we're going to do is we're going to replace n minus 1 pick 2 with this formula. So in this case, n, that first number, is not n, it's n minus 1. So everywhere we see n, we're going to have n minus 1. Okay, so we would have, again, n minus 1 here, and then factorial around the outside. And we also know that r is basically 2. So everywhere we see r, which is right here, we'd put in a 2. So minus 2 equals 90. Okay, let's simplify that a little bit. N minus 1 factorial. On the bottom, n minus 1 minus 2 is going to be n minus 3 factorial. Okay, so now think back to what we've done previously. We have factorials in an equation. Well, in order to deal with that, we need to expand our larger factorial. So think which factorial is going to be larger? N minus 1, right? So start with that one. N minus 1, 1 less than that, n minus 2, 1 less than that, n minus 3, and then factorial because we've now reached the 1 in the denominator, n minus 3 factorial. And that means now we can divide those two common factors, and we are left with, might as well expand that, n squared minus 2n minus 1n, so minus 3n plus 2 equals 0. Okay. Now, if you look at that, we basically have a quadratic equation now, but it doesn't do us any good to factor that until we have 0 on one side. So we are going to subtract 90 over, so we'd have 2 minus 90, which is negative 88. And now that it's equal to 0, we're going to factor it. Should always factor if we're doing this right, because n has to be an element of the whole number, so it shouldn't come out to be some decimal. Okay, so multiplies to negative 88. Immediately I think 8 times 11, right? So let's try that. 8, 11. Okay, in order to get negative, the signs are opposite. Bigger one has to be negative to get negative 3. Okay, branch each one off. N plus 8 equals 0. So n equals negative 8. And n would equal 11. Okay, because n has to be an element of the whole numbers, negative 8 won't work, but 11 is good to go. Okay, so what to use when, right? My experience is the fundamental accounting principle is a good fallback position, but once in a while you can use NPR as long as there's no funny business happening like restrictions or repetitions or, anything like that. So when in doubt, I'd probably use fundamental accounting principle. All right, good job everyone. Hopefully you're ready to do the assignment, and thank you so much for listening. We'll see you next day.